In this video, I will derive the translational energy of a system given its partition function. Assuming the Boltzmann distribution, the total energy of a system that consists of a large number of particles can be expressed in terms of the partition function. E equals -n times dl1q over d beta. E is the total energy, n is the total number of particles, q is the partition function, beta is 1 over kBt. This total energy can also be expressed in terms of temperature by using d beta over dt equals -1 over kBt squared. We have energy equals n times kb times t squared times dl1q over dt. And this kb is the Boltzmann constant. So these two equations are just general expressions of the total energy in terms of partition function. And the partition function for a chemical system can be the product of the translational partition function, the rotational partition function, the vibrational partition function, and the electronic partition function. Usually the first three Q are referring to the motion of the nuclei, and the last one is referring to the partition function of the energy level of the electrons. And then if you plug in this product into here, the natural logarithm of Q, the product becomes a sum, and therefore the total energy equals the sum of the translation energy, rotation energy, vibration energy, and electronic energy. And again, the first three terms are referring to the kinetic energy of the nuclei in three categories: translation, rotation, and vibration. And the last one is the electronic energy. Let's work on the one-dimensional translational energy. And first, we need to derive the partition function of the one-dimensional translation. It's the sum of e to the power of negative epsilon beta, and epsilon is n squared h squared over 8ma squared. A is the dimension of the one-dimensional box, m is the mass of the particle, n is the quantum number, and can be from 1 to infinity, h is the Planck constant. And then I'm going to use this integral to approximate the sum and change the lower limit from 1 to 0. And this approximation is fairly good. And then we just need to integrate this. I also changed this n to x. This is just for kind of just simplicity here. And then this Gaussian function of x is an even function. Therefore, this integral from 0 to infinity is equal to 1/2 of the same function, the integral of the same function from negative infinity to positive infinity. Again, this is because the integral value of the left half equals the integral value of the right half of the Gaussian function. And then what we need to do is to set z squared to be this whole thing here in the Gaussian function. So z squared equals h squared x squared over 8ma squared times beta. This is just to simplify this Gaussian function. And if that's the case, then x is equal to the square root of 8ma squared over h squared beta times z. So I'm replacing this x with this function of z here. And I'm replacing this Gaussian function with e to the power of negative z squared. And because this part is a constant, so I can take it out of the integral, so I combine this two later. And how about this integral? This integral is the square root of pi. I derived this in another playlist titled Math for Physical Chemistry. So now we have the expression of the one-dimensional translational partition function which is simply the square root of 2 pi m a squared over h squared beta. And because we have a squared h squared inside the square root, so I can take a over h out. And then we get back to this very general expression. Again, this Q can be translational, rotational, vibrational, or electronic partition function. And the Q can also be the just the total partition function as well. Just you can use this equation for any kind of situation. So I'm going to using this for the one-dimensional translation here. Now, the energy of one-dimensional translation is equal to negative n times d ln q over d beta. So d ln q, so this is my q over d beta. And pay attention here, we are taking the logarithm of this thing, and this becomes the sum of ln beta to the power of negative half and ln 2 pi m to the power of 1/2 times a over h. Okay, it becomes the sum. And the second term is a constant, which does not depend on beta. Therefore, we have just ln beta to the negative half here. Again, it's supposed to be d ln beta to the power of negative half plus d ln the square root of 2 pi m times a over h. But again, the second term is simply 0. And then this part is simply just n over 2 beta, which is 1/2 times n times kpt. How about three-dimensional translational partition function? This is simply the product of the one-dimensional translational partition function in 3 dimensions. And assuming we're dealing with a particle in a 3-dimensional box with dimensions a, b, and c, and then we have just this same expression, except for this a can be replaced by b or c. And then we have the product of the 3 one-dimensional translational partition function. We get this 2 pi m over beta to the power of 3/2 times this volume of the box over h to the power of 3. This volume is just a times b times c. And then we plug in the expression of q into, again, the expression of the energy equals negative n d ln q over d beta. So this is q. And then you can easily tell that other than this term, the other terms do not depend on beta, so they disappear. And then we have just simply just d ln beta to the power of negative 3/2 over d beta. The result is 3/2 n kpt. So in the end, we can tell that the average one-dimensional translational energy is half kpt. The average three-dimensional translational energy is 3/2 kpt.